Hi, coming to you today from the old observatory at my mom's place out in the back. My uncle Alan used to, look for Pluto back in the day out here. Um, anyway, I wanted to talk to you today about the scientific revolution of the 17th century, the 1600s. There's sort of two scientific revolutions in a sense in that period of the 1600s and the 1700s. In the 17th century, the 1600s, you get the scientific revolution that I want to talk about today, the one that culminates with Isaac Newton. And then in the next century, the 1700s, the 18th century, you get sort of the empiricist revolution where scientific methodology kind of takes over. And that becomes a big part of the culture wars. That's not exactly what's happening in the century before that, though. And I think that it's important I think there's a lot that we can get out of looking at the sort of rationalist scientific revolution of the 17th century, the 1600s. One of the things to notice as we go through, I think, is that although nowadays there's this clash of science and traditional beliefs, religion, and there was certainly the same clash going on in the century that we're going to look at today. But the scientists and other thinkers of the 17th century weren't necessarily, many of them were very religious. And this is a century in transition where you really don't have a real clear sense of a distinction between being a scientific naturalist on the one hand and having religious ideas on the other. In fact, a big thing that's going on for all of the thinkers in the 17th century is this connection between sort of mathematics and the natural world. You've got the necessity of mathematics and you've got the contingency of the natural world that we see and that we look at when we're doing empirical science. So God comes into play here for a lot of these thinkers. But getting back to what I was saying before, we think of nowadays of biology, I think, and also astrophysics as two sciences. Physics kind of a central science for us. The science we think of is really doing kind of a lot of the cutting edge knowledge production. And then, of course, evolutionary biology, very controversial for the last 100 years, well, 200 since Darwin. And so in the century that we're looking at today, the 17th century, the 1600s, that role, the role of the provocative science that's shaking everything up, the science that's really driving everything else, and that's the big influencer on what's going on, is astronomy. And so we're going to look at a little bit of the history of astronomy today, which is a wonderful, wonderful topic. But I think also we should come away today with some sense of the importance of astronomy on so many levels, including the aesthetic level and philosophical level in terms of the way that we see ourselves. So let's take a look at some of that stuff today. I want to show you, in fact, to be specific, I want to go over two scientists, Galileo and Newton, and then I want to talk about a political theorist, Thomas Hobbes, and a composer, Johann Sebastian Bach. And I think after I go over Galileo and Newton, and again, what it means to say that you have a sort of rationalist scientific revolution during the Baroque period, then I believe you'll see quite fluently how Hobbes and Bach both reflect that century. So it is the age of astronomy. Now, like many other things, this takes a while, a long time coming. And in fact, it's Nicholas Copernicus in the Renaissance period who is the first to really revolutionize astronomy. In fact, we talk about the Copernican revolution. It was Copernicus who really overthrew the old Ptolemaic model of the cosmos. And Copernicus then, who made the, if you'll pardon the pun, really sort of earth-shaking step, who suggested that the universe was revolving around the sun and not around the earth. That is, he proposed replacing the geocentric model, geocentric says the earth is at the center of the universe, with the heliocentric, that is, that the sun is at the center of the universe. So Nicholas Copernicus did this, and he too is a truly revolutionary figure. After Copernicus, you got a wave of new astronomers, a big new generation of astronomers, because of the impetus that this Copernican revolution had provided. And so you get a rejuvenation of, for example, astronomy, including naked eye astronomy, as well as a rejuvenation of the practice of making star charts. And a lot of these people, by the way, did astrology as well as astronomy, as was true also of ancient astronomers back in in ancient classical times. Kepler, I'll just mention because there's one theme that we're having here is seeing that nature is uniform throughout the cosmos. Kepler, prior to Galileo, showed that the orbits were in ellipticals, they weren't in perfect circles. A traditional Ptolemaic or Aristotelian or Platonic astronomy from the ancient classical period would say that these were sort of perfect Platonic structures up in the celestial realms, which were more perfect than down here in the earthly realm. So when Kepler says these are ellipticals, they're not perfect circles, and this is the direction that things are kind of moving in. And at the same time, you get, not coincidentally, I mean, there's a really serious interest in optics. And so astronomers and lens grinders obviously have a close relationship. This is back in the day when a lot of people did this for themselves. Galileo actually made significant improvements on the design of the telescope by introducing refracting mirror, for example. But what's happening to people in this period is that they're looking through the telescope and the microscope. And by the way, telescope and microscope aren't opposites, right? They're both magnifying the light, so you can take a look at what you're looking at. And so they're seeing all kinds of things that no one could see before. And so this is also, the technology is driving a lot of the science here, because these lenses are really blowing everyone's mind. Galileo built his own telescopes. Some of the scientists and other worthies who would come to visit Galileo were afraid to look through the telescope. They thought if they looked through the telescope, something bad might happen to them. Let's talk about Galileo some more. I would say Galileo and Newton, the two that I'm going to cover today, I think are arguably the two most important, certainly physical scientists of the 17th century. And again, Galileo, first of all, making observations with his telescope. And he saw what's easy to see if you have good glass these days, binoculars. You can see the mountains on the moon. And he also figured out how to look at the reflections, the shadow of light, as you may have done if you've looked at an eclipse or something, to look at, and he was observing sunspots. So Kepler showed that you have elliptical orbits. Galileo sees that there are rough mountains on the moon, irregular mountains, and he also sees that the sun has sunspots and whatever they are, but there are irregularities on the surface of the sun. So what's interesting about that in general then is that was good evidence that the sublunary realm, if you will, the realm down here on Earth underneath the moon, and the superlunar area that Plato thought was, and Aristotle sort of thought of as sort of a realm of heavenly spheres that approached formal perfection, that these two realms were in fact largely the same, that rocks, and you can see this from meteors. The ancient thinker Thales also examined meteors, and it looked like these were rocks that were like rocks from here on Earth. So that's an important sort of movement, this idea that that nature is uniform throughout the universe, that everywhere you go in the universe, nature follows the same kinds of patterns, and eventually we'll say the same kinds of laws. Galileo, the second bullet point there, he's measuring stars. Now, the old way, the way that the ancient Greeks used to do it too, of course, was just to measure every, a celestial object once and then do it again 6 months later, and you've got an angle, and then you can triangulate and see how acute or obtuse the angle is. But they didn't know how far things were, and Galileo started to get a handle on that. And this is something, let me step out of that for a second too. The two things in the modern world that had to be discovered, one was deep time, how old everything is. And we see this, of course, even right up into the 19th century. Many thinkers, Christian thinkers in Europe, for example, thinking that the Earth is maybe 10,000 years old. It was the geologists, actually, the 18th century, the 1700s, who were studying glaciated terrain. And they were the ones who first figured out that what they're looking at is really, really honking old, way, way older. Because, see, human beings aren't used to, we didn't evolve to think about factors in the millions or distances or units of millions. I mean, that's something sort of really sort of abstract to us, a million miles. So that was never obvious. And so another really big contribution of Galileo and his tradition of astronomy was he was one who showed that no, actually there are enormously huge distances in space. That was something that hadn't been appreciated before. And as I say, this notion of deep time and deep space. And so if we want to understand also the attitude of people in older times, we have to realize that they didn't understand those things. They didn't have those concepts of those very, very large numbers as part of nature. All right. Another thing, the third bullet point, he saw the moons of Jupiter look like a little mini solar system hanging out there. It's what you could call a planetary system, a planet and its moons. Of course, now we know there's lots more moons, but those are the ones you could see. The thing, though, again, that was also something that was really highly significant, because you remember we were talking before about the heliocentric and the geocentric models of the cosmos. Is everything revolving around the Earth, or is everything revolving around the sun? Well, a really important question there is everything revolving around something, some one thing? And when Galileo showed that Jupiter had moons revolving around it, well, then obviously everything isn't revolving around Earth, and everything isn't revolving around the sun either, because Jupiter's got stuff revolving around it. And so you see this movement towards a kind of spreading out and naturalizing of the picture of what we're looking at when we look at the universe. He was tried for saying that the Earth moved, when it seemed as to the church, to the Inquisition, as if obviously the Earth did not move. Newton later gets in trouble when he shows that the orbits, his equations for the orbits work best if he assumes that space is a vacuum or a near vacuum. The church didn't like that because it seemed as if God didn't have anywhere to stand. But Galileo was very important and very famous. So nothing really bad could be done to Galileo by the Inquisition. He was still able to write, but he was under house arrest, and he was somewhat broken by that as well. Although he was an older man then, so it's hard to know. But he even at the time, the day of the trial, he whispered under his breath, "Nonetheless, it moves." Now we want to see then very quickly here how Galileo is a precursor to Newton. Galileo is kind of where it all comes from, and Galileo is definitely where Newton's kind of getting it, because Newton's looking at Galileo's work on the celestial bodies, the movement of the heavens and the status of the movement of the Earth, and he's seeing that what Galileo establishes is there are these mathematical principles that are uniform and necessary, and they are throughout science. I mean, you could say that Newton generalized Galileo's physics from just the celestial bodies to all of nature, but Galileo actually did that already himself. Galileo understood that these formal mathematical laws and patterns were all through nature. But that's what I was talking about before. These thinkers, Galileo and Newton, certainly, they're not atheistic thinkers. They think that what this is sort of proof of the existence of God, really, is sort of the way that they read it. And a lot of philosophers of the time, such as Spinoza, Leibniz, Descartes, I mean, all major rationalist philosophers think the same thing. So this new science to them is actually a science that's very imbued with religion, because it looks as if this transcendental level of sort of mathematical organization, just like Plato, remember this is post-Renaissance, what is it the rebirth of? Again, this Platonic rationalist sensibility. And so it was Galileo then who paves the way for Newton. Galileo says you can you could formalize these relationships. What do you mean formalize? Well, 3 plus 3 equals 6 is a formalization. So I mean, I've got 3 pancakes over here and 3 pancakes over there. I've got 3 battleships over here. I got 3 battleships over there. Formalize. It's not about pancakes. It's not about battleships. It's just about sets of 3. Okay, that's the idea. So this is the rationalist end of the scientific revolution. So let's take a look at Isaac Newton. I think teaching early modern philosophy, well, I don't think this, I do this. Teaching early modern philosophy, I always include Isaac Newton because Isaac Newton is a very important philosopher, just like Charles Darwin is also a very important philosopher when we get to the 19th century. Philosopher, that is, saying things of real metaphysical and epistemological import. Also, remembering that the Principia is what everybody calls it, the Principia Mathematica, which he published in 1687, that's a good date to remember that Newton published the Principia in 1687, because a lot of stuff depends on whether it's before or after Newton. A lot of things that a lot of other scientists and philosophers say is influenced by Newton. So if you can remember that Newton's at the end of the 17th century, late 1680s, if you can get around there, I find that's useful in terms of orienting myself towards a lot of other history of science and other intellectual history. So now, if you are intimidated by this stuff, don't be, because what we're talking about here is very common sense. But let's look at that second bullet point about force and motion. And he has a formula there that acceleration is force of a thing divided by the mass of the thing. These look like arbitrary things, but actually they're very commonsensical. But I wanted to go over this quotation I have from him there. It says this concept is purely mathematical. This concept force, he says, is purely mathematical. For I am not now considering the physical causes and sites of these forces. This is an important thing that it's easy to miss about Newton. Newton doesn't have any theories. Newton says he doesn't have theories. He's like Sherlock Holmes. He scorns theories. Newton just gives us descriptions of things. That's what he does. But Newton gives us mathematical descriptions of forces, like the force of gravity that I'm going to talk about in a second, because it's a useful one to help us understand. So Newton's not explaining why there's gravity or anything like that, or where it comes from, or how it works. He's not saying how it works. He's saying, well, this is what happens, and this is the equation that describes the force. But that's what he does. And he says, you know, look, I'm telling you about these mathematical principles. I'm giving you their formalizations. I'm giving you the equation for gravity. But this isn't a theory. I'm not telling you why there's such a thing or how it works. I have no idea. So people miss that about Newton, I think. All right, go on. Yeah. Where is it being like that? Here we go. Okay. So that's important. He and Leibniz developed the calculus about the same time. You can see that's in the air, as they say. Someone was about to do this. And I won't go on about that. You have too much calculus in your life already. They had a terrible fight. Leibniz, I wouldn't know, but a lot of mathematicians say Leibniz is a little bit better. But anyway. Now, and then as far as astronomy goes, look at that second to last bullet point, 1668. Spectroscopy. Okay, spectroscopy. So elements, you know, your periodic table of the elements, and elements have kind of a light signature. And so if you take the light from a celestial object and you run it through a prism and break it up into the light that composes it, you can read off of that the atomic elements that compose, and molecular as well, the structure of the celestial objects that's emitting the light. And so, of course, you can see that's completely essential. And in fact, that's really one of the main technologies of astronomy today is actually looking at what things are made out of by performing spectroscopy on the light. Okay, and so finally, then let's look at that gravity. Again, one thing to notice is that it's really pretty common sense. Proportional to the product of the masses, you take the two masses of the thing and multiply them. But then inversely to the square of the distance. Okay, the massier something is, the more, the farther away it is, the less. And again, notice that that is a universal law. That is, what does that mean? That means that that explains the gravitational attraction between two leaves that are circling each other on the surface of a puddle. And it explains the gravitational attraction of two galaxies that are circling around each other, attracted to each other in the vastness of space, and everything in between. So it, like mathematics itself, Newton's physical laws are transcendental. This gravity applies to any mass, any two massy objects. And what he does is, and remember we mentioned calculus, you can plug in whatever values you want, but he gives you the equation. That's what Newton does. So you get this picture from these scientists, Galileo and Newton of the 17th century, of a world that's kind of a clockwork world. It's a mathematically organized world, and the aesthetic values are precision, but there are also some other consequences of thinking the way that they do that have interesting consequences for political theory. So let's take a look at that. Another slide on Newton. Newton, the theologian, as I was saying, Newton, I mean, it's not a speculation. Newton left behind many hundreds of pages of theological writings about the nature of God. Newton was a real believer, Isaac Newton. And Isaac Newton thought that in showing things like the equation for gravity, the gravity relation, that he was revealing the face of God. These were the revealed face of God. Just like the classical Greeks, again, the Renaissance, the Rinascimento of the ancient Platonic thinking, that when we look at the world and we see its organization, what we're really doing is glorying in God. And as I say, you might notice the philosopher Spinoza. I talk about him, and I guess in the other video that I'm going to post this week. Newton, again, no theories whatsoever. Like Sherlock Holmes. Sherlock Holmes has no theories whatsoever. He says whatever is left after everything else is shown to be false. Newton gives us these transcendental descriptions. Any two massy objects, right, will fit into this. Second to last bullet point there, notice, as I said at the beginning, this is a scientific revolution that is not by any means an atheistic revolution. The scientific revolution of the next century, 18th century, the 1700s, will be atheistic in that sense that it will say that if there isn't empirical evidence for entities, then they are doubted or ought not to be countenanced, which leads to atheism. But Isaac Newton's view, as I hope you see by now, doesn't lead to atheism at all. In fact, I think one way of getting our minds around the thinkers of the 17th century is that they really do think that the universe is kind of the mind body of God. They think that the mind of God has to be involved in causation as well. Okay, so two examples then of thinkers who are not physical scientists and how they were influenced by this rationalist science of the 17th century. The first is Thomas Hobbes, who published his book Leviathan in 1651. Hobbes is famous for saying that people have to be under some kind of sovereignty. Here's how Hobbes's argument works. Let me just do it real quick, and then you'll have it. So Hobbes reasons thusly. He says, first, that freedom is the ability to move towards the object of your desires. And then Hobbes says that in a state of nature, a state of anarchy, as much of the world was in during these post-Reformation wars, remember. He says in those kinds of conditions, you do not have maximum freedom, not under anarchy, because under anarchy, it's the war of all against all, and it's terrible conditions, and everyone has to do everything they can just to survive. So, Hobbes says, if you define freedom as the ability to move towards the object of your desire, the pursuit of happiness, then Hobbes says you're actually freer under sovereignty. What's that? Under a system of laws and a structure that can enforce the laws that guarantee certain rights and responsibilities, not least your right to not be killed. As he says, at a minimum, you have no loyalty to any government that doesn't guarantee your right not to be killed, for example. And so Hobbes starts off liberal political theory real early here, right? Way back in the 17th century. But what's Hobbes doing? Hobbes is adopting from Galileo this idea that the universe is made out of matter and motion. That's where he's sort of getting it from. So now we can take a little bit of a closer look at that then. So you have, according to Galileo, you have these objects, celestial bodies are all moving. There are various theories about momentum and inertia and stuff, but basically the idea is you're going to keep moving. So the universe is made out of these things that are moving along their paths. And the universe is made out of matter and motion. Hobbes is very ahead of his time in the late 17th century in saying that, well, we ought to take this physical natural science and apply it to social science, to the study of human beings. I mean, that's really the ultimate humanism, right? You say, well, gosh, I think that human beings are part of this physical world that we're studying as well. And notice then that if we adopt from the astronomers the idea that the universe is matter and motion, we get a kind of atomism. The universe is all these little atoms in motion. And modern political theory, not coincidentally, reflects this idea that you have a lot of reasonably autonomous, reasonably self-interested individuals sort of pursuing their own interests. And that's your starting point for doing social science. And that is Hobbes' starting point. He says, if all these people are out there just struggling to survive, they'd be a lot better off under a government. Hobbes goes further than that. That's Hobbes' political side. How about his side in philosophy of mind? Hobbes says he's a materialist about the mind. He says, maybe memory is preserved in the brain by sort of spring-like structures that vibrate in the way that we forget the memory is deteriorating the same way that the vibrations of the springs will deteriorate as other vibrations come through. He had the technology of his time, winches and bellows and pulleys and things, and hydraulics. So he talked about the brain using those kinds of analogies, the same way we use the computer as an analogy today. Nothing new, just using the technology that he had. But he was convinced that sort of naturalist physical approach was the right one. And again, very much inspired by the astronomers, very much taken by their vision. And remember, he's before Newton publishes, right, by a while. And expanding that to the natural sciences. And then finally, Bach. Now, let me just say another thing. Somebody was saying at the Zoom meeting the other day that they were looking forward to doing the composers. We are going to do composers. Today I'm going to talk about Bach as a Baroque composer. However, doing this learning at a distance, at the moment, I've kind of concluded that we can't really sit and listen together. I am going to give you some Bach links, if you look in the links, where you'll be able to listen to some music and see some examples of what I'm talking about. And I suggest you do that because it's very interesting music. But I'm just going to incorporate these composers into these more general treatments of sort of the tenor of the times, I think, unless I figure out a better way to do it. I am evolving. It's just me, and I don't hardly know how to work these things at all. All right. Where are we? We are, but Bach anyway. The last thing we're going to talk about, and then we're done. So we call orchestral music classical music in slang, but actually classical music refers to a particular period from sort of the middle of the 1700s into the 1800s the Baroque period we call Baroque music. So we have Baroque music, classical music, and then Romantic music at the beginning of the 19th century. And those are just sort of three periods of orchestral music. There is orchestral music now in the 20th century, but I'm not going to talk about that. These are the basics. Bach is your basic Baroque composer, Mozart your basic classical, and Beethoven your basic Romantic composer. So what does it mean to say that Bach is a Baroque composer? He is the intensely rationalistic artist. We think of Baroque as a slang, a stylistic term. We think of Baroque as very busy. Well, Bach has this atomistic kind of approach, and he wants to take the patterns of a melody, and then he'll do things like run it upside down, run it backwards, exploring these formal possibilities, sort of modal, if you will, possibilities in these formal patterns that he has. You can actually, and I'll give you some links on this, there's actually computer generated music that sounds very similar to Bach. And as I say in the last bullet point on the slide there, Mozart and other composers of the next century to some extent are reacting against this hyper sort of rationalism, which they found didn't have enough soul, didn't really have enough swing. I love it. I think it's great music, but it is this pointillistic music that the pleasure is largely intellectual because you're listening to the way that the themes and the melodies are then deconstructed and reconstructed and woven back and forth by the composer. So, and we can see this, I think I have another slide. Yeah, we can see this in the scores. We will compare when we get there, Bach scores from the 17th century with Mozart scores from the 18th century with Beethoven scores from the 19th century, and you'll see the scores look really different. Scores very important for orchestral music. We lose track of that today, but a big part of this whole art form is writing the score, writing out the score, and looking at the scores is an important part, I think, of appreciating this art. So that's another thing that I would recommend to you. Again, going back here to the Bach slide. Okay. All right, so we're good. Okay, so I wanted to show you two things today. The first thing was that when we talk about the scientific revolution of the 17th century, this is really a rationalist revolution. It's not atheistic. It's still very interested in the status of God because it is very interested in the status of mathematics and transcendental organization in the world that identifies with God. And so it's an interesting transitional period. As I mentioned in the other video I'm going to post this week, sometimes people think of philosophers of this period as maybe not being honest about what they think about God. I think they are honest believers and are using God as a technical term of art for dealing with some of these rationalist insights that we looked at today in the works of Galileo and Isaac Newton. It's all one big ball of wax. You can't separate the philosophers from the scientists, from the social theorists, even from the composers. And that's true of all the centuries that we look at. So I encourage you to, lots of different interesting things to look in here. I encourage you to follow your bliss on that. And I'll talk to you again soon. Bye-bye.